Perfect. Yeah, thank you guys for coming and listening to my my thesis defense. So today I'm going to be talking about the population characteristics and movement of blue catfish in the Kansas River. Understanding the characteristics of a population is critical when managing any wildlife or fisheries resource. Fisheries managers use population characteristics such as abundance, growth, mortality, or size structure to understand how management is being, how population is being affected by current management strategies, or to track how a population changes throughout time. For closed systems such as reservoirs or lakes, or this beautiful East Texas pond, the spatial scale used to investigate and manage the population is restricted by the confounds of the closed system. However, in open systems such as rivers, additional information regarding the spatial extent of the population is required, as individuals have the mobility or ability to move within a connected river network. Species that exhibit small home ranges or limited mobility can be investigated and managed at a smaller localized scale. However, mobile species, such as many large river specialists, use multiple bodies of water throughout their lifetime, and this requires adopting a spatial scale that incorporates the movement and dispersal patterns of the population. Many river systems today have anthropogenic barriers like dams, and this limits the movement of fish and further complicates the selection of a spatial scale for mobile species. So in summary, understanding the movement and dispersal patterns is essential when investigating or managing a population in impaired waterways, particularly for mobile large river specialists. The blue catfish is a large river specialist native to the Mississippi River Basin. This species is highly mobile, with tagged individuals traveling hundreds of river kilometers throughout their lifetime. Blues have been in the past considered the most mobile, but also the least understood North American ictulurid, and this has spurred on a lot of recent investigations. Most blue catfish investigations have focused on large river or reservoir populations, with fewer studies investigating large river tributary systems. The fast growth and the large maximum size of blue catfish makes them popular among both harvest-oriented and trophy-oriented anglers. The distribution of blue catfish has increased in recent decades. For example, these figures provided by USGS depict the established range of blue catfish in 2013 versus 2020. In a few regions of the United States, such as the Eastern Seaboard or the state of Kansas, blue catfish continue to expand their established range. This is in part due to state wildlife agencies stocking blue catfish in reservoir environments to provide additional angling opportunities for the growing number of blue catfish anglers. Introductions have been problematic in some systems, and blue catfish, as a result, are considered invasive in some systems outside of their native distribution. Evidence of reservoir entrainment has occurred across the distribution as well. Entrainment is the passage of a fish through a dam structure, and in this case means from a reservoir environment to a river environment. Reservoir populations have both contributed and supplemented downstream populations as well as established new populations. So as blue catfish increase both among anglers and also their distributional expansion, fisheries managers are increasingly interested in developing a holistic understanding of blue catfish ecology across the various systems they occupy, including large river tributaries. The Kansas River is a large tributary to the Missouri River, which is located on the northwestern periphery of blue catfish's native distribution. This project was prompted by anecdotes of increased blue catfish abundance, as well as angler interest within this system. Catfishing is a long-lived tradition in the lower Kansas River where their study occurred. Here are two commercial fishermen from the late 1800s boasting their morning's catch of a pair of 100-pound catfish. And 140 years later, there's not a lot that has changed in some aspects, and that is that there's still a dedicated group of anglers that enjoy this resource. But despite its reputation for producing large trophy fish and abundance of fish as well, no historical data regarding this population exists, and this has limited fisheries managers' abilities to appropriately manage this population. As a result, Kansas River has been regulated by a statewide creel limit that has been mainly implemented to prevent overharvest. This project was initiated to address multiple gaps in information regarding Kansas River blue catfish. Over the past 30 years, Kansas Department of Wildlife, Parks, and Tourism has stocked 1.3 million blue catfish in reservoirs throughout the state of Kansas, resulting in established self-sustaining populations and a number of reservoirs, including 4 that are highlighted here in close proximity to the Kansas River. Multiple tagged fish from Milford and Tuttle Creek Reservoir, which are the furthest west, have been entrained during the time of this study. And this has provided evidence of reservoir contributions to downstream river systems. However, the degree to which the population or these populations are contributing to the Kansas River, and in particular the lower Kansas River, remains unknown and is an information gap that needs to be addressed. The box region on this map indicates the lower Kansas River where our study occurred. And within this region, there are 3 anthropogenic barriers. Sorry about that. I don't know how to hang. New phone system, pardon me. So within this lower segment, there are 3 anthropogenic barriers that may act as a barrier to fish movement. As we know, blue catfish are mobile large river specialists. And so this is another gap in information that needs to be addressed. The Topeka and Johnson County weirs are water intake structures for local municipalities. They're very similar to each other in size and stature, and perhaps limit the movement of blue catfish or other species during times of low flow. However, during times of moderate or high flow, these are not a barrier to fish movement. Bowersock Dam in the middle of our study area is a low-head dam that's been shown to limit the upstream movement of a number of fish species, including invasive Asian carps and or carp species, as well as blue suckers. So we use these 3 dams to further break up the Kansas River into 3 river segments to investigate these different aspects of our project. Segment 1 was from the Missouri River to the Johnson County Weir. Johnson County Weir to Bowersock Dam was segment 2. And segment 3 was between Bowersock Dam and the Topeka Weir. The size and stature, or in other words, the passability of these dams for fish to move through, creates a gradient of habitat connectivity between the Missouri River and the broader river network and this tributary system. For example, segment 1 has full connectivity in the Missouri River and the broader river network, as there's no barriers of entry or movement. Because of the presence of Johnson County Weir, segment 2 is considered to have intermittent connectivity, which is dependent on high enough discharge for fish to be able to pass through this dam. Bowersock Dam is an endpoint for upstream fish movement, and this leaves us with segment 3 as an isolated tributary population. The lower Kansas River provides a unique opportunity to examine the impacts of river network connectivity for a tributary population of a large specialist, or large river specialist, in this case, blue catfish. We had 2 main objectives of this study. First, we wanted to provide initial characterization of the population characteristics within this system. Just go ahead and unhook the phone so that doesn't happen again. We also wanted to use this data to draw inferences on the response of a tributary population with and without connectivity to a main stem river system and the broader river network. The second objective was to describe the spatial distribution of this population. Recall back to the beginning slides, understanding the movement and dispersal patterns of a large river specialist is critical to understand the spatial scale that needs to be used in future management or investigations. Under this objective, we sought to characterize the movement and dispersal patterns of blue catfish in the Kansas River, as well as quantify the contributions from outside sources, such as reservoirs and the Missouri River. With these 2 objectives in mind, I'll now describe briefly how we collected our data. Fish were sampled during May through August of 2018 and 2019. Approximately 50 otoliths were collected from each segment. Otoliths are the inner ear bone of fish and are regarded as the best structure for aging catfish. In addition, we used otoliths for microchemistry analysis, which I'll touch on in just a bit. Otolith collection was separated into juvenile and adult fish using 400 millimeters as a point of division, as this is the earliest size that is known to be sexually mature in southern states. All fish that were not used for otolith collection were then tagged with a T-bar Floyd tag, so that if anglers recaptured this one of our fish, they could call in and notice or provide notice of where it was captured. We primarily use low-frequency electrofishing, as this is the adopted standard for collecting catfish in a number of reservoirs. We also use bank poles, which is a form of passive angling gear. And this was used to increase the number of large fish in our sample, as low-frequency electrofishing tends to be biased towards individuals smaller than 1 meter in length. We also attended catch and release catfish tournaments at the confluence of the Kansas and Missouri rivers. And this was, we attended these in order to provide additional sample size of tagged fish, as well as to develop an understanding of how this resource is being used by this demographic of anglers. I'll first describe the population characteristics chapter or objective. I use 5 commonly used metrics to assess differences in the population characteristics across the river gradient: size structure, growth, mortality, condition, and relative abundance. Water conditions between sampling years varied greatly, and I wanted to briefly highlight this before moving on to results. Here's a hydrograph that depicts the daily mean temperature in red and the daily mean discharge in black. In 2018, we experienced very low discharge at with a mean under 3,000 CFS, and very high temperatures with the mean above, or with the highest daily mean peaking above 32 degrees Celsius or 90 degrees Fahrenheit. 2019 was characterized by moderate temperatures, but highly variable water conditions with several flood events and a peak flow of 100,000 CFS. The vast difference in water conditions contributed to some temporal variation in several of the characteristics that I'm going to describe, and I just wanted to briefly highlight this before moving on. To investigate size structure, I use proportional stock density, or PSD, which is a commonly used metric for size indices, particularly for sport fish management. This table here depicts the values for PSDQ, or quality length, PSDM, memorable length, and PSDT, or trophy length. Throughout the remainder of my presentation, I'm going to use a red line that indicates Bowersock Dam as a way to orient you to the data. We observed in size structure that segments 2 and 1 were very similar, especially with memorable and trophy size fish. However, segment 2 did have a slightly higher memorable and trophy size fish, higher proportion of those fish. And this is better illustrated through this length frequency plot. So this plot depicts the number of fish on the x-axis and the ascending length bends on the y-axis. The shaded region depicts the fish that were categorized as memorable or trophy sized fish. As you can see, segment 1 and 2 had a number of these larger fish and were relatively similar, whereas segment 3 had few memorable fish and no trophy length fish, indicating a truncated size structure above Bowersock Dam. So in summary, segments 1 and 2 were similar to each other and yielded higher proportions of memorable and trophy fish, and segment 3 had a truncated size structure. To investigate the spatial variation in growth, I used the mean back-calculated length at 3 life stages. At age 3, blue catfish are considered juveniles. This age class was used to describe the somatic growth of fish, as gonadal development had not yet occurred. The mean age of sexual maturity for blue catfish across their distribution is at age 6. This age class was used to describe the growth of fish during and up to gonadal development. Lastly, age 10 was used to represent the growth of adult fish several years after sexual maturity. The following plots are going to, on the y-axis of the following plots are the back-calculated length at age, and on the x-axis is the river segment with the red line indicating the presence of Bowersock Dam. For ages 3 and 6, we observed significantly greater back-calculated length at these ages for segments 3 compared to segment 1. Segment 2 fell in between these two segments. However, by age 10, regardless of location, fish obtained relatively equal length at age. So overall, results suggested that there was higher somatic growth for reaches upstream of Bowersock Dam than those that had full connectivity in the Missouri River. To assess mortality, I used weighted catch curves to calculate annual and instantaneous mortality. Fish were considered recruited to the gear at age 6. This table depicts the annual mortality, or A, and the instantaneous mortality, Z. Similar to the previous characteristics, Segments 1 and 2 were very similar to each other in mortality estimates, and above Bowersock Dam we saw a slightly higher mortality. For condition, I compared relative weights across spatial and temporal scales. This plot depicts the distribution and mean relative weights for each segment in each year, with 2018 using dashed lines and solid line in 2019. Within a given year, mean relative weights did not vary across the river gradient. However, we did observe variation among years, with 2018 yielding lower relative weights than 2019, or lower water conditions yielding lower condition. The observed temporal variation is likely contributed then to the variable water conditions that we observed on the Kansas River. So overall, we observed no spatial variation in condition. To assess relative abundance, I used the number of fish captured per hour of low-frequency electrofishing to represent the catch per unit effort, or CPUE. This plot depicts the log-transformed CPUE data for each segment in 2018 and 2019. The proportion of unsuccessful sampling events, or electrofishing runs that resulted in no blue catfish, is enumerated below these box plots. Overall, we observed extremely variable catch rates, especially for stock length and substock length fish. Stock length fish. Overall, however, we observed just no variation across the spatial or temporal scales, indicating that relative abundance is consistent across the river gradient. Overall, our results from this chapter, or this objective, suggest that segments 1 and 2 below Bowersock Dam function differently than segments 3, or above Bowersock Dam. Reaches above the dam had higher somatic growth and higher mortality, while segments below the dam had higher trophy potential and lower mortality. Condition and relative abundance did not vary spatially throughout the study area. These data suggest that connectivity with the Missouri River allows fish to live longer and obtain greater lengths, despite having slower somatic growth rates than segments above the dam. However, the documented accounts of blue catfish being entrained from reservoir environments suggest that there's more at play within the system than just connectivity to the Missouri River and the greater river network. For example, substantial influxes of blue catfish to segment 3 from reservoir environments may have contributed to the higher somatic growth rates and the higher calculated mortality. So drawing additional conclusions on the mechanisms behind the spatial variation observed requires additional information regarding the spatial distribution and specifically the movement and dispersal patterns, which brings me to the second objective of our study. To describe the spatial distribution of the population, I used two commonly used fisheries techniques. Data provided by recapture tagged fish was used to verify the passage of fish through the 3 anthropogenic barriers on the Kansas River. This data was also used to provide insight onto the distance and orientation of individual movement events, seasonal movement patterns, angler harvest rates, and also provide empirical evidence of Kansas River fish using other river systems. I also used otolith microchemistry analyses to describe the natal origin, or where a fish originates from, and the environmental history of a fish, or where a fish spent its life. Oops, I'm sorry, I got a little behind. I'll first discuss the Mark-Recapture portion of the study. This plot depicts the distance and orientation of all recapture events from both our efforts as well as angler call-ins. The x-axis depicts the date of recapture. All recaptures were between the months of April and October for both years. On the y-axis is the distance traveled by an individual, with negative values representing a downstream movement and positive values representing an upstream movement. I further divided this into 3 river segments and used different line types to indicate the location of recapture. Solid lines representing the Kansas River, dashed lines representing the Missouri River or a Missouri River tributary, and dotted lines representing the Delaware River. The Delaware River flows from Perry Reservoir, which is in segment 3, flows into it, segment 3. Overall, we observed several large downstream movement events from fish initially tagged in segments 1 and 2. Our furthest movement event in this project was from a fish originally tagged right below Bowersock Dam, and within 2 years had traversed Johnson County Weir, entered the Missouri River, and overall traveled nearly 500 river kilometers in a downstream orientation before being recaptured by an angler in the Osage River, which is a tributary to the Missouri River in central Missouri. The Johnson County Weir was the most traversed structure and was traversed by 6 fish in both upstream and downstream orientation. We observed no upstream movement of Bowersock Dam, and only one individual, which was a juvenile, was entrained through Bowersock Dam. These last 2 points highlight and verify the previous assumptions of the connectivity along the river gradient between tributary habitats and the greater river network. From our angler recaps, we had 5 unique water bodies represented, including the 4 that I've already described, as well as the Platte River, Missouri. Overall, our results suggest the use of connected river systems, particularly for fish in segments 1 and 2 or below Bowersock Dam. However, we did observe some fish within segment 3 using a tributary to the Kansas River, the Delaware River. And to depict this, I'll zoom into our plot here and eliminate all movement events that are greater than 50 kilometers. And if we look at segment 3, there's a number of fish that moved upstream into the Delaware River where they were caught at Perry Spillway. We documented both local and transient fish. Fish that were traveled less than 1 kilometer between capture events are indicated by solid lines along the value of 0. Fish in segment 1 showed a variety of both upstream and downstream movements, whereas fish in segment 2 mainly moved in a downstream orientation. This suggests that Bowersock Dam prohibits and also may discourage upstream movement of blue catfish in segment 2. We also observed seasonal movement patterns, which have been previously described in several large river studies, and that is that blue catfish move upstream into tributary systems during the spring and summer months and downstream in the fall and winter months. We also observed different harvest rates from our angler recaptures. The Kansas River had a lower harvest rate than the Delaware or Missouri River, suggesting the Kansas River has lower harvest rates than adjacent river systems. The second method of describing the spatial distribution for this population was using otolith microchemistry analyses, which I'll briefly describe for those of you that may be a little unfamiliar. Trace elements, such as strontium, are deposited in the otolith of a fish, and this reflects the ambient water chemistry of the environment which a fish occupies. Luckily for fisheries managers, otoliths remain largely unaltered by metabolic processes, and so this allows us to retrospectively identify the occupied environments of a fish throughout its lifetime. The image to the left of the screen is a cross-section of otolith that we use for aging and microchemistry analysis. And the center region of the otolith is the nucleus, and this represents the earliest stages of life for the fish. We use this region to describe its natal environment or its natal origin. As a fish ages, the otolith continues to grow and depositing trace elements as well. In this study, the regions outside of the nucleus were used to describe the environments occupied by a fish throughout the remainder of its lifetime, or its environmental history. We use a laser to ablate a transect line through the natal origins and the remainder of the otolith, and then are able to quantify the strontium-calcium ratio using a piece of machinery called an inductively coupled plasma mass spectrometer, or ICP-MS. The data that's produced looks similar to this, and we are able to isolate the natal origins and the environmental history of a fish by relating to the ablation transect of the otolith. We then use this data to relate the otolith values to the ambient water chemistry of the bodies of water within our study area. So in this example, this individual has natal origins indicating the Kansas River, and then moves into the Missouri River for a large part of its life, with perhaps a brief foray back into the Kansas River before being captured. So a key aspect then to otolith microchemistry is understanding how trace elemental ratios vary across a given study area. To do this, I collected multiple water samples from 16 sites along the Kansas River gradient, as well as from the 4 tributary reservoirs and their affluences, and the Missouri River, both upstream and downstream of the Kansas River confluence. Water samples were grouped by water body and assessed for differences in strontium-calcium ratios. Clinton Reservoir, which is the only reservoir with a basin south of the Kansas River, represented the lowest strontium calcium ratios. The Kansas River and the upper Kansas River were also significantly different than the remainder bodies of water and from each other as well. In this study, we combined these two reaches of the Kansas River for several reasons. First, the upper Kansas River encompasses a relatively small proportion of the overall Kansas River gradient and represents the regions between Milford and Tuttle Creek reservoirs. Additionally, this was the only body of water that had strontium calcium ratios that were higher than the Kansas River. And the objective of the study was to quantify outside contributions. And the upper Kansas River is still part of the river gradient. The three northern reservoirs and the Missouri River had significant overlap in their water chemistry. And to overcome this, we use Mark-Recapture data to further inform the interpretation of our results. For example, fish captured below Bowersock Dam, segments 1 and segments 2, that had signatures indicating this overlapping region were designated as Missouri River origins, or environmental history, as we know that entrainment through Bowersock Dam was minimal during the time of this study. For segment 3 above Bowersock Dam, values representing this overlapping region were designated as a northern reservoir, as we understand that Bowersock Dam prohibits upstream movement of fish, and this eliminates the possibility of a Missouri River signature. Next, I use a linear regression between the water and otolith strontium calcium from known source fish to predict a range of otolith values for the ambient water conditions of each environment. I use the 95% confidence intervals from this linear regression to categorize the strontium calcium ratios of otoliths into the different occupied environments. Strontium calcium values that occurred in overlapping regions were described as indistinguishable, which can be visualized here. The regions between the two horizontal dashed lines represent an overlap in the 95% confidence intervals for Kansas River and the Missouri River. From this point forward in my presentation, these will be described as indistinguishable regions, as I was not able to confidently say the environment which these data points came from. So then fish were grouped by the different river segments, and they were analyzed for natal origins and environmental history. First, I'll discuss the natal origin results. To summarize natal origin data, I examined the proportional distribution of natal origins for each river segment. We'll start with juvenile fish, or those under 400 millimeters. The majority of fish collected in segments 1 and 2 had natal origins indicating the Kansas River, particularly for segment 2. It's important to note that juvenile fish tend to be less mobile than adult fish, and as a result, we would expect a higher proportion of Kansas River natives, especially in reaches that may have limited connectivity to adjacent systems, such as segment 2. However, this was not the case in segment 3. Only a quarter of those collected in segment 3 had natal origins indicating the Kansas River, with 50% of those, or the majority of those, originating in one of the 3 northern reservoirs. For adult fish in segments 1 and 2, they displayed nearly identical distributions of natal origins. A third of fish in these segments originated from the Missouri River, and a third originated from the Kansas River. Natal origins indicating Clinton Reservoir were also observed in these segments, particularly in segment 2. For reaches below Bowersock Dam, equal contributions of the Missouri and Kansas Rivers occurred. Similar to juvenile fish, half of adult fish collected above Bowersock Dam originated from reservoir environments, with few individuals originating from the Kansas River. To summarize, reaches below Bowersock Dam had relatively equal contributions from multiple river systems, while half of those above Bowersock Dam originated from a reservoir system. Several days before my written thesis was due, an interesting event occurred, which I wanted to highlight here. The Army Corps of Engineers dewatered Tuttle Spillway below Tuttle Reservoir, and in the process of doing so, salvaged 70 to 75,000 pounds of fish. They estimated that over 80% of these fish were blue catfish. I'll also note that there's a low-head dam below this spillway, which means that all of these fish originated from the reservoirs. This provides additional support for the large contribution of reservoir fish to downstream river systems, including the lower Kansas River. Next, I'll discuss the environmental history portion of our study. To summarize the environmental history, I created 4 lifelong movement patterns. The following 4 examples will use a horizontal dashed line as a lower threshold for a Kansas River signature. Values above this line represent the Kansas River, values below represent an outside system, in this case, a Missouri River. The first movement pattern were immigrants. Immigrants were those that originated from an outside system and had a one-time movement event into the Kansas River where they remained until they were captured. Resident fish were those that originated in the Kansas River and remained in the Kansas River until capture. Returning immigrants were those that originated within the Kansas River, moved to an outside system, and returned to the Kansas River at time of recapture. By default, if a fish was not categorized as these 3 options, it was because they were a transient fish. A transient fish was one that had multiple movement events and was classified as a transient regardless of their natal origins. Similar to natal origins, I used the proportion of each movement event across the 3 river segments. So the results will look similar, or the figures will look similar. So we'll start once again with juvenile fish. Recalling on our natal origin results, we would expect a high proportion of juvenile fish to display a resident pattern, as juveniles tend to be less mobile. Resident fish did comprise the highest proportion of movement patterns for each river segment, particularly in segment 2 once again. Segment 2 also had the highest proportion of transient fish and no classification of immigrants, or those that had a one-time movement event into the Kansas River. Segment 3 had the highest proportion of immigrant juvenile fish, all of which originated from the reservoir environments. For adult fish, relatively low proportions of resident fish were observed across all river segments. Reaches below Bowersock Dam contained a much greater proportion of transients and returning immigrants compared to reaches above Bowersock Dam, suggesting the use of a broader river network. Perhaps the most notable difference was between upstream and downstream of Bowersock Dam was the high proportion of immigrant fish and the low number of transient fish in segment 3. This suggests that segment 3 has unidirectional movement from reservoir systems and acts as an endpoint for reservoir immigrants. Similarly to our population characteristics results, these data suggest that the spatial distribution and movement and dispersal patterns for reaches above and below Bowersock Dam are different. Above Bowersock Dam, we observed the use of a single tributary, the Delaware River, and high contributions from reservoir systems. This system, we also have evidence to suggest that this system acts as an endpoint for reservoir immigrants. The population below Bowersock Dam uses a much broader river network and had relatively equal natal contributions from the Kansas and Missouri rivers. Overall, a small proportion of resident fish were observed across the study area, and this suggests that management strategies that are limited to the Kansas River will largely be ineffective due to the high amount of variability of where these fish came from and where they're going to. The results from both portions of this study suggest dividing the Kansas River for future management by using Bowersock Dam as a point of division. Downstream reaches currently have a high trophy potential and low mortality. We also have evidence to suggest they use a broad river network. These results, coupled with our evidence that suggests minimal angler harvest in this segment, suggest that the current statewide regulation is adequate at providing a trophy quality fishery. However, the high harvest rate observed in adjacent systems such as the Missouri River suggests that management actions into the future may rely on reflecting the population's distribution in order to perpetuate this trophy quality fishery. A broad management scale would require jurisdictional cooperation as well, as downstream river reaches such as the Missouri River are under a different management organization than the Kansas River. reaches upstream of Bowersock Dam may be suitable for relaxed harvest regulations. Our results suggest that segment 3 acts as an endpoint for reservoir fish, which may lead to overabundance into the future due to the high amount of contributions we observed from reservoir systems. Spillways below the 3 northern reservoirs are accessible to the public and within our observations commonly used by harvest-oriented anglers. Increased creel limits at these locations would provide additional opportunity for consumptive users that may be restricted to bank angling, as well as provide potential solution for mitigating the overabundance of entrained fish if that occurs into the future. The results of our study are applicable to broader management of blue catfish and other large river specialists, particularly those that are also game fish. Various studies have illustrated the importance that tributary habitats play for main stem river populations of large river specialists. In a similar fashion, our results illustrated the importance of main stem contributions for a tributary population. We also highlighted the difference in population characteristics between tributary systems with and without connectivity to a broader river network. Our results join the growing body of literature that highlights the importance of unimpaired river networks for large river specialists. So future management of blue catfish and other large river specialists relies on adopting strategies which are not confounded by a single river, but reflect various environments incorporating a river network framework. I had a lot of help over the past few years, particularly braving the Kansas River, which can be a beast at best. So I wanted to highlight these folks who provided help in the field as well as insight on the project. I also wanted to thank Kansas Department of Wildlife, Parks, and Tourism and those that are in that organization for initiating this project, entrusting me with the resources to conduct the research, and also ultimately helping me further my career in fisheries management. And I also wanted to give a special shout out to Jake Warner, who was there every step of the way and helped me a lot on the Kansas River and data analysis. So thanks, Jake, for all your help. And with that, I'll take any questions.
Thanks, Quentin. Great job.
Thank you.
These Zoom environments, it's hard to give a round of applause, but I think we're all